Conduit fill is an important aspect of electrical installations. Based on the information provided, it appears that you are dealing with questions about conduit fill, pull box ratings, and grounding practices. The National Electrical Code, or NEC, specifies the maximum number of conductors allowed in a conduit of a particular size. For a 3/4-inch electrical non-metallic tubing, or ENT, you can have a maximum of 6 number 12 American wire gauge, or AUG, conductors. This is according to the NEC. With the situation described, you have 5 number 12 AWG conductors in the 3/4-inch ENT. This includes 2 hot conductors, both black, for 220 volts 20 amps circuit, 1 ground conductor, green, shared between the 2 circuits, 1 hot conductor, red, for 120 volts 20 amps circuit, and 1 neutral conductor, white, for the 120 volts 20 amps circuit. Therefore, having 5 number 12 AWG conductors in a 3/4-inch ENT is within the code. Moving on to the pull box rating, the pull box should be marked with its maximum fill capacity and the number of conduits it can accommodate. It is important to check the manufacturer's specifications or the box itself for this information. The NEC provides guidelines for sizing pull boxes based on the size and number of conduits entering and exiting the box. The pull box must be large enough to provide adequate space for the conductors and any splices or terminations within the box. Ensuring the pull box is properly sized is crucial for safety and compliance. Now let's discuss grounding. It is acceptable to share the ground between the 2 feeder circuits as long as the ground wire size is based on the amperage of the largest circuit. In the described case, both circuits are 20 amps. Although they are both 20 amp circuits, the NEC requires the ground wire to be sized based on the overcurrent protection of the largest circuit feeding the equipment at ground. Table 250.122 in the NEC provides the minimum size of equipment grounding conductors for grounding raceway and equipment. For a 20 amp circuit, the minimum size of the grounding conductor is number 12 AWG copper. However, since there are multiple circuits sharing a common grounding conductor, the size of the grounding conductor must be increased to accommodate the potential fault current from all the circuits. According to the NEC, when multiple circuits are run in the same raceway or cable, a single equipment grounding conductor can serve all the circuits, provided it is sized according to the largest overcurrent device protecting any of the circuits. In the described situation, where there are 2 20 amp circuits, it is acceptable to use a single grounding conductor size for the largest circuit, which is 20 amps. Therefore, a number 12 AWG copper grounding conductor is sufficient. However, it is always a good practice to consult the NEC and local codes to ensure compliance with all applicable requirements. Furthermore, it's essential to ensure that all grounding connections are made properly and securely to provide a low impedance path for fault current. Now, addressing the inspector's concerns. The inspector may have concerns about the difficulty of adding another conduit due to space limitations. They may also want to ensure the pull box is adequately sized and accessible for maintenance. To address these concerns, it is recommended to contact the inspector and discuss your situation. Provide them with the specifications for the ENT and pull box to demonstrate compliance with the code. Explain the challenges of adding another conduit and why it would impact your project costs. Propose a solution that meets both the code and the inspector's concerns, such as using a larger pull box or finding an alternative route for the additional conduit, if possible. By communicating effectively with the inspector and providing them with the necessary information, you can often resolve any concerns and avoid unnecessary expenses. In summary, having 5 number 12 AWG conductors in a 3/4-inch ENT is within the code. Sharing the ground between the 2 circuits with a number 12 AWG ground is also acceptable, but using a number 10 AWG ground provides an extra margin of safety. The pull box needs to be checked to confirm it can accommodate the number of conduits and conductors you have. And it is essential to address the inspector's concerns by providing them with the necessary information and proposing a solution that meets both the code and their requirements. The National Electrical Code, or NEC, is a comprehensive set of standards that govern electrical installations in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electricians, contractors, and inspectors to be familiar with the NEC to ensure that electrical installations are safe and compliant. One of the key aspects of the NEC is conduit fill. Conduit fill refers to the amount of space occupied by conductors within a conduit. The NEC specifies the maximum percentage of conduit fill allowed for different types of conduits and conductors. This is to prevent overheating and ensure that conductors can be easily pulled through the conduit. The NEC also provides guidelines for sizing pull boxes based on the size and number of conduits entering and exiting the box. The pull box must be large enough to provide adequate space for the conductors and any splices or terminations within the box. Proper sizing of pull boxes is crucial for safety and compliance. Grounding is another important aspect of electrical installations. Grounding provides a low impedance path for fault current to return to the source, which helps to protect people and equipment from electrical shock. The NEC specifies the requirements for grounding different types of electrical systems and equipment. It is essential to follow these requirements to ensure that electrical systems are properly grounded and safe. In addition to the NEC, local codes may also apply to electrical installations. Local codes are often based on the NEC, but they may also include additional requirements specific to the jurisdiction. It is important to check with the local authorities to determine which codes apply to your project. When working on electrical installations, it is always best to consult with a qualified electrician or electrical engineer. They can help you to ensure that your installation is safe, compliant, and meets your specific needs. The information provided here is for general guidance only and should not be considered as a substitute for professional advice. Electrical work can be dangerous, and it is important to take all necessary precautions to protect yourself and others from electrical shock. The purpose of grounding is to provide a low impedance path for fault current to return to the source. This helps to protect people and equipment from electrical shock by ensuring that overcurrent protective devices, such as circuit breakers or fuses, trip quickly in the event of a ground fault. Grounding also helps to stabilize voltage during normal operation and reduce electrical noise. The NEC specifies the requirements for grounding different types of electrical systems and equipment. These requirements are based on the type of system, the voltage, and the potential for fault current. It is essential to follow these requirements to ensure that electrical systems are properly grounded and safe. There are two main types of grounding systems: grounded systems and ungrounded systems. Grounded systems have one conductor that is intentionally connected to earth, typically the neutral conductor. This provides a reference point for voltage and helps to stabilize the system. Ungrounded systems do not have a conductor intentionally connected to earth. Instead, they rely on insulation and isolation to prevent ground faults. Ungrounded systems are often used in critical applications where a single ground fault should not cause a disruption of power. Equipment grounding is another important aspect of grounding. Equipment grounding involves connecting the non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and motor frames, to the grounding system. This provides a path for fault current to return to the source in the event of a ground fault, which helps to protect people from electrical shock. The size of the equipment grounding conductor is based on the size of the overcurrent protective device protecting the circuit. The NEC provides tables that specify the minimum size of equipment grounding conductors for different size circuits. It is important to use the correct size grounding conductor to ensure that it can safely carry the fault current. Grounding electrodes are used to connect the grounding system to earth. Grounding electrodes can be made of metal rods, pipes, or plates that are buried in the ground. The NEC specifies the requirements for grounding electrodes, including the size, material, and installation depth. It is important to install grounding electrodes properly to ensure that they provide a low impedance connection to earth. Grounding connections must be made properly and securely to ensure that they provide a low impedance path for fault current. Grounding connections can be made using a variety of methods, including mechanical connectors, compression connectors, and exothermic welding. It is important to use the appropriate connection method for the application and to ensure that the connection is properly tightened and protected from corrosion. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electrical shock. GFCIs work by monitoring the current flowing in the hot and neutral conductors of a circuit. If there is a difference in current between the two conductors, it indicates that current is leaking to ground. When the GFCI detects a ground fault, it quickly interrupts the circuit, preventing electrical shock. It is important to test GFCIs regularly to ensure that they are working properly. GFCIs should be tested monthly by pressing the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced. Surge protection devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges caused by lightning, power line disturbances, or switchy events. SPD work by diverting surge current away from sensitive equipment and back to the source. SPD are available in a variety of types and sizes, and they should be selected based on the specific application and the level of surge protection required. It is important to install SPD properly to ensure that they provide effective surge protection. The NEC provides guidelines for installing SPD, including the location, wiring, and grounding requirements. Electrical safety is paramount, and it is important to take all necessary precautions to protect yourself and others from electrical shock. Always work with a qualified electrician or electrical engineer when working on electrical installations. They can help you to ensure that your installation is safe, compliant, and meets your specific needs. Never work on live electrical circuits. Always turn off the power at the circuit breaker before working on any electrical equipment. Use insulated tools when working on electrical circuits. Wear appropriate personal protective equipment, such as safety glasses and gloves. Follow all applicable codes and standards. If you are not comfortable working on electrical circuits, do not attempt to do so. Hire a qualified electrician to do the work for you. Electrical safety is everyone's responsibility. By following these precautions, you can help to prevent electrical shock and ensure that electrical installations are safe.